All right, everybody, we're going to get rolling today. Please welcome Dr. Ann Barcomb, and she's going to be talking about fairness testing.
Hi, good morning. Well, I was just introduced, but as it's implied, I do research, and so I just want to do a brief plug, first of all, for some research. There's some papers over there if you feel like potentially participating in research on writing bug reports. So totally unrelated to this talk, just, hey, I need some research subjects. And actually, specifically, what I'd like is people who are unfamiliar with making bug reports to try to make a bug report and see whether the process we're using helps people. So that was a very quick aside that I promised to do on behalf of a grad student. So now let me get right into the topic of today's lecture, which is fairness testing. And that's an emerging area of research that has been less involved in industry so far on formalizing aspects of fairness into a series of repeatable tests that can be included as part of the development process. And the fundamental concept is that different users should be able to achieve similar outcomes when they are working with the software. And this is the definition of software fairness that is drawn from the research, that it is a property of learning-based systems that aims to ensure that the software does not exhibit biases. And there's a few different aspects of that. We'll get into some of those in more detail. But the main point is that we should get similar outputs or similar program behaviors regardless of who is using the software. And software bias has a couple of different ways that we can look at it. And one example is individual bias. In this example, we can consider a sentiment analyzer software that determines the emotional state or the situation being described in some text and describes that as either a positive emotion or a negative emotion. Obviously, there's more varieties. Like we could have sadness or anger. And in this figure, the output, the sentiment, is different in this case depending on the gender of the noun. So if the text says man, it's seen as a positive sentiment, and if it is seen as woman, it is seen as a negative sentiment. So this is an illustrative example of what gender bias at the individual level would look like. This is not any specific software, but this is just an example of natural language processing, how you would see individual level bias. So fairness testing is considered to be a non-functional software property, like, say, speed. And individual fairness means that the software should treat similar individuals similarly. And a system satisfies the group fairness attribute if subjects in protected and unprotected groups have an equal probability of being assigned to a particular outcome. So we just looked at an example of individual fairness, and group fairness looks at it more from a perspective of groups and whether they have equal probability. So here's an example of group bias. In this situation, we are comparing different groups, in this case, a doctor and a nurse. And here we're seeing that the doctor is perceived as being positive for being excited, and we're seeing that the nurse is being perceived as negative for being excited. And this is an example of group bias. And this is where there's no inherent difference between the groups that would make it so that we wouldn't want the same outcome for each group. So It's not like saying, the serial killer was excited. Obviously, that's a group of people we maybe don't want to see excited. This is two groups that essentially have no real difference between them, except that we know that one job tends to be more likely to have women occupying it, another more likely to have men occupying it, and that is probably the reason that this model, this example model, has inferred the differences. So group fairness, we're looking at whether these groups tend to be overrepresented by certain categories of people based on protected attributes. So that can be gender, that can be race, that can be sexual orientation, that can be age, any one of those attributes where discrimination is relatively common and where that group has a large representation of a particular category. So that's where group bias is. Group bias is more of an inferred bias, whereas the individual bias is one of those recognized categories. So just as we can do traditional software testing at different parts in the system, for example, we could do a unit testing, we can do integration testing. For fairness testing, we can do several different places. We can do it on training data. We can do it on the machine learning programs, the models, the frameworks, non-machine learning components, but it is mostly used for machine learning, and most of the work that has been done to date has been on the outputs of machine learning models. We know, of course, that machine learning is largely vulnerable due to the inputs, and so people have definitely looked at the input side of things as well, but most of the current research has been on the outputs. Yeah?
What's going to be the difference between a program, a model, and a framework?
Yeah, that's just, this is drawn from a specific research paper. But I think we're looking at the program would be essentially when you have specific models, you can tune it, do the fine tuning with different hyperparameters and so on. And you could say employ, like here we have a fairness repair algorithm. So you can try to apply something. So after you've built the model and then you're trying to essentially be applying the model, and then the model itself would be before we're trying to apply it. Why they have frameworks separated, I'm sorry, I don't know. I think it's just, and you can see it has no types of fairness testing there. This is, interestingly enough, one of the things that one of my grad students is working on. What is a framework versus a library versus all these other things? And the problem is that these words are not used consistently, even in research. So I'm sorry, I can't quite answer that part. So different types of training data bias. We have feature bias, and this is where the training data has a strong correlation to sensitive attributes, such that even when you remove those sensitive attributes, the unfairness is still present. So one example of that, sorry, I'm just trying to get my notes to be a little bit smaller here so I can actually read them. So one example of that, I do remember this one, is in 2016, Amazon created a same-day delivery service that was only available for certain zip codes. And those zip codes that were not eligible for same-day delivery were actually strongly correlated with certain racial groups and considered bad neighborhoods according to their algorithm. But on the face of it, it just looked like, oh, this is a zip code. We can do same-day delivery to this zip code, and we can't to this zip code. But if you actually looked into it, then there was reason to suspect that it was actually discrimination against a particular demographic group. Label bias occurs when factors that are unrelated to those determination of labels influences the process that generates the outcome labels. So machine learning models are created with data collected over an extended period, and during the data collection process, labels are typically assigned by either human annotation or by algorithms, thus introducing the potential for human and algorithmic biases to be encoded in the labels. So this is another form of bias that we can look for. And selection bias, of course, is when there is an unexpected correlation between the sensitive attributes and the outcome. And this occurs when the sampling of training data introduces an unexpected correlation. So for instance, a research paper in 2022 analyzed data sets that were used for lie detection and discovered that there was gender bias within them. So specifically, the data set had a much higher proportion of data for women labeled as lies. So then the model essentially inferred not that these were the lies and these were the truths. What it inferred was these women sounding voices are more likely to be liars, because the data was not balanced. So in machine learning programs, it's pretty common to include data processing scripts that will manipulate and transform the training data for downstream tasks. And this processing itself can have impact on the fairness of the software. There are certain pre-processing methods that can introduce fairness bugs, while other methods may improve software fairness. And this one is not very strongly researched. It's pretty new. But for example, real-world data sets can contain missing values, and there are different techniques to fill in these missing values, and some of those have been shown to be more likely to introduce bias than others. So there's all these different things we have to think about, even when we're just collecting the data that goes into the model. And needless to say, a lot of times this isn't considered. Then in the program itself, we have the hyperparameters, and that's parameters such as the learning rate or the choice of optimizer that specifies details about the learning process. And this also has been found to sometimes lead to bias. Again, this is another area that has been less strongly considered. As I mentioned, most of the research has focused on looking at the models and being able to identify if the model has biases or not, and then to be able to basically flag it for humans. Much less research has gone into, research has gone into the how can we improve the data that's going in, but like what we can do in the middle has been a lot less studied. So as fairness has become increasingly an important requirement for some software systems, there's the option to include fairness repair algorithms. These are also called bias mitigation algorithms. And these are basically where you can specify which things you would want to allow for discrimination. And here I mean in the non-negative sense, in the fact of discriminating between different things, and which things you would not want to do that. So, for example, we would expect that students who have completed their homework are going to maybe score higher in their exams. And so we don't want to say that if our model finds that to be the case, that we should throw that data out. On the other hand, we do want to be able to flag certain attributes as protected attributes, which we are not expecting to see any difference between. And this one I thought was absolutely a surprise to me, but there apparently are different suppression algorithms that can influence whether or not the bias. And it's just all about when we are saving some parts of the model and we are reducing some of that, particularly for use on mobile devices. There are different types of approaches that can do a better job of preserving the information that we want. I'm sorry, this is not my computer and I'm having a lot of trouble getting it to scroll. So essentially, pruning and quantization can amplify gender bias when, say, classifying hair color in a computer vision data set. They found that pruning the model there, basically there's ways to do it with more and less bias. And this is really outside of my work because I work primarily with natural language processing. I just wanted to mention this to say that it's not only about language, it's also happening with, say, facial expressions and hair color and so on. Now, for the model testing, we do have the white box testing that tends to try to find fairness bugs by examining the training data or the internal structure of the machine learning model. So this is used when we have access to the internal parts of the model. But black box testing or opaque model testing is what we have most frequently, where we do not have access to the internal side of the model, and we do not necessarily have explainability. So we have to basically be able to detect fairness in order to see whether or not, based on the outputs to particular problems that we give it. And this is where most of the research has been done to date. And it typically relies on statistical measurements to be able to identify fairness bugs. So now we've looked at all the different things that can be tested, which there are a lot, but most of them are not in use. So now let's look at how we could, for example, put fairness testing as part of a workflow. So if we look at all of the different areas, this would be how we could apply things at different levels. So this is how we would do it for, say, a machine learning software that is building upon established machine learning models. So in this process, the developers would establish the specified fairness conditions or the fairness requirements, and these largely stem from individual fairness and group fairness definitions. And then based on this, we can conduct tests, and then we can try to do some debugging and repair. And then once those fairness conditions have been satisfied, then the software could be deployed for use. And we could continue to employ runtime monitoring to see if the software responding to new data is being changed in any way. So I'm now going to go over just some of the different types of fairness testing that we have developed with different researchers. This is not me, this is like just the field in general. So one type, a lot of these tend to be pairwise testing. So Astrea does a co-reference resolution where it tries to identify a pronoun in a particular sentence. So for example, this sentence, the farmer was passing by, he, she, they told the baker that the document was signed. And then we want to basically see which one is going to be filled in here. Another variant of that is we would say the doctor or the nurse took a plane to, and then the pronoun is masked, hometown. And then finally, we might have the sentiment analysis, which is the examples that I saw earlier, where we have either the CEO or the cleaner feels enraged. And what we would basically try to do here is mutate sensitive attribute-related words using alternate tokens. And then we want to see what the results are from essentially having this filled in. So for example, with the farmer, the accurate co-ref systems should solve the noun and have he and she both as equally likely options. So this test case would contain these two different options, and the system should have no greater difficulty assigning one gender or the other. And a failure would occur if the sentence is unable to be resolved with, say, she in this case. This is another tool that we have. It's the Crow's Pairs data set, and it is used primarily for measuring stereotypical biases in language models, and it has 9 different types of biases available. And each example is divided into a sentence pair, and one sentence is about a disadvantaged group and the other is about an advantaged group. And the first sentence can either demonstrate or violate a stereotype. So here are some examples. And the second sentence should involve minor modifications to the first one. And here we have, for instance, a more stereotypical sentence, and then a less stereotypical sentence, and then an example of what type of stereotype or non-stereotype is being demonstrated. And this is just a data set that can be used to design tests. So how it's actually deployed is often just to see, are we more likely to come up with the stereotypical sentences than the less stereotypical sentences. So most of the existing data sets that we have are, first of all, about natural language processing, and they are mostly about gender, race, and sexual orientation. But we are starting to see some data sets and some tools that are being developed for other types of bias. So I did mention the one that looked at hair color. Also, one of my colleagues, for instance, has a student working on voice recognition, specifically comparing whether trans voices and cis voices are equally likely to be identified. Because there has been studies, for example, about cis men and cis women, and the comparison there, that cis women's voices are less likely to be recognized, but that has been, we're now looking into some other areas as well. And for instance, a paper recently came out that created a data set that had some additional types of bias. So they looked at colorism, they looked at disability, neurodivergence, colonial bias, ageism as well. And so this is some of the new work that's coming out to try to increase the number of different types of bias that we can test for in these models. So one of the questions that often comes up is who should be involved in fairness testing? And well, obviously, I think that people who are working on the code obviously should. But too often what we see is that the people that are working on the code, releasing the code, those companies, are not really concerned until somebody in the bigger community raises a problem and says, oh, hey, look at what this data set, or look at what I'm getting out of this model. And then there's usually some media attention. The model is withdrawn, and then after a while it's quietly released, hey, we fixed it. So I do think that there's absolutely communities should be involved in looking at the models and being able to say this is biased. We shouldn't be basing decisions on this model. And this is also part of a user-centered design. But we also need to be involved in this long before these types of models are released on the public. So we should be looking at it from within the companies, but also we should have policymakers considering, because the risks of when these biased models are deployed, say, to make decisions about, say, which neighborhood should be policed or who should get a longer sentencing. These are real life examples, of course, where products have been deployed and they did have, in both cases, racial bias, and then decisions were made based on these algorithms. So this is where I think that pretty much everybody potentially has a role to play in trying to ensure that these models, if they are used, are not full of a bunch of biases that honestly can be easily determined by testing. So I've talked a lot about the research, and I've not talked about how can you do this in your own organization, and that is because we don't actually have a how-to guide yet, but we're working on one. So if you think that you would like to review some type of guide on how to implement fairness testing within your own organization or work, we are looking for people to be testing this guide in about 9 months. And I would love it if you would get in touch with me about, oops, we are one too far. There we are. That is my email address. And yeah, we are very interested in trying to make this a much more practical rather than a theoretical approach, because most of it has been just researchers, so that people who want to employ this sort of testing in their organizations before releasing models have the opportunity to be able to do it with, hopefully, similar to how you might set up your unit testing or your integration testing, and you could just set this up as one part of your process. So this is, I know I'm pitching more research, but this one is related. This one is absolutely related. And I mentioned a few different papers. Some of the ones that I wanted to highlight are mentioned here. These are all relatively recent papers on fairness testing. So the second paper, for instance, is the one that came out with this data set that was involved many different types of fairness that hadn't been tested before. And this last one, I have a whole bunch of bonus slides on that I didn't know if I was going to have time to get to or not. And I think I probably won't, but I did want to talk a little bit about her work. This is a doctoral thesis, and it actually is a way of looking at software within the broader idea of impact. And so it's not just about fairness testing, it's about how is this software going to be used, who is going to be using it, and so on. And she provides essentially a step-by-step guide of thinking about potential software and its impacts before such software is actually built. So it's I found that a very interesting piece of research that I'd love to see, but it's slightly out of scope, so that's why I didn't cover it here.